Okay, we are now live. Hello and welcome everyone out there on the internet watching. You are joining us for the European Planetary Sciences Conference in Cascais, a suburb of Lisbon, Portugal. And with me are a variety of asteroid scientists, and we're going to talk about how these rocks in space are fabulous scientific opportunities and occasional threats to the planet Earth, but not right now, mostly. I'm going to ask each of you to introduce yourselves, and I'll start with you.
Hi, I'm Cristina De Santos from Rome, and I'm working on a mission that is the first mission that visits two asteroids, the most massive in the network. That's so I will do my best to answer the question about that.
Thank you.
My name is Alberto Cellino. I have studied the physical properties of asteroids for now several years. At present, I'm particularly involved in the development of the Gaia mission because we expect revolution in astrophysics science and that, and I'm responsible for some of the pipelines in the production for observations of solar system objects.
Hi everybody, I'm Paolo Tanga from Observatory de la Côte d'Azur in Nice, France. I'm responsible for the data treatment of solar system objects observed by Gaia, and usually my main task is study physical properties of asteroids.
Now, the Dawn mission is one that we've heard a lot about in the United States. With CosmoQuest, we've done a variety of online events jointly with them. And it's a fabulous mission that is using an ion drive to slowly but surely creep its way from the very large asteroid Vesta to the even larger asteroid Ceres. These are two, I've heard them referred to as planets at this meeting, two very large objects that have fascinating geology and formed either side of that line in the solar system that defines where water became ice during the solar nebula when the planets and asteroids and other small objects in our solar system were forming. Now, the Gaia mission, unfortunately, we haven't brought quite as much attention to because, yeah, and I was hoping that you could bring us up to speed on the Gaia mission.
Well, simply speaking, Gaia is something that could be described as the forbidden dream of a remote observers of asteroids, because you can do the kind of observations that you do also normally from the ground, but with an enormously improved limit capability, both in astrometry, in spectroscopy, and in photometry. So this is something, and this will produce results that cannot be easily obtained from the ground. Also because of the fact that we are in the space, of course, there is no such things. And so this is the reason why it is so important.
Yeah, we can remember maybe that Gaia was not built to study solar system because mainly it was a mission that was thought for exploring our own galaxy, so well beyond the limits of the solar system, stars and the galaxies, structures and dynamics. But soon when it was when the project was taking shape, it was realized that it would have a huge impact on the solar system as well. So it will be a revolution for the study of stellar astrophysics, galactic astrophysics, but also for solar system objects.
And unlike Dawn, which is journeying through the solar system, Gaia is more of an orbiting observatory.
Yeah, in fact, it's orbiting not around the Earth. It is, I would say, a kind of equilibrium situation, away from the Earth and direction opposite to the Sun, in a particular point in space, where you can stay about without too many perturbations and in a very stable environment. I mean that there are no huge thermal variations, for example, and from that position, it has the stability that is needed to observe the sky with that accuracy.
And this is the same Lagrange point where they're trying to put the James Webb Space Telescope.
Yes, exactly.
It's this magical is the wrong word. Anything that's complex mathematically sometimes gets called magic. It's that awesome place where the forces between the sun and the earth balance out just right, that an object can stay in orbit. You're not the sun Earth, you're the Earth Moon Lagrange point.
No, it's the sun.
It is the sun Earth one. Yeah, so it goes sun, Earth, Gaia.
Yeah,
yes.
1.5 million.
And so that's a place where if something breaks, you're in trouble, but you can get there much quicker. You actually only launched less than a year ago, and you're already getting data back.
Yeah, in fact, the travel to the Lagrangian point from the Earth is pretty fast. Let's say that in a couple of weeks, Gaia was stabilized in a trajectory around the Lagrangian point. But then the verification of the instruments, the calibration took a lot of time due to the accuracy required by these procedures to exploit these capabilities of measurement, of which maybe we can speak more.
So what is your favorite new science result that's come out of the mission?
Well, probably in the field of asteroids. By the way, asteroids will be the bodies of the solar system that will be the most important targets of Gaia, because the major planets are either too big or too bright to be observed. So what is left is the large population of asteroids. Possibly the most important result will be the determination, the accurate determination of the masses for a number between 100 and 150 objects, for which we will have also the determination of the size and the shape, and so we will derive the average densities. We will have also a taxonomic classification, so we could, for the first time, interpret taxonomy in terms of density, this kind of thing. So this is a measure. And then this is qualitatively very new and important. Then quantitatively, there will be a lot of data on a very large number of objects. We will have a taxonomic classification for a number of the order of 200,000 asteroids of the Mendel. We hope to be able to have to be able to record and invert the commentary, the brightness variations over a number of these level of objects, so that we have spin properties, shapes, this will be measured. And then, of course, since the major feature of the Gaia mission is the astrometric capability, so the capability to measure the movement precision, the position in the sky of the object, we will have an improvement of the order of 100 in the accuracy of the orbital elements of the object. So it could be also another measure of development.
It's easy to lose track of how amazingly difficult it is to measure the masses of these objects. They orbit the sun, which has such a bigger mass that you can pretty much ignore the mass of the asteroids when you solve orbital equations. And so typically the only way we've been able to get at the mass of these objects is to sort of guess. We get hit here on Earth by meteorites. We find out some of them are iron, some of them are basically just rocky. And we know looking at asteroids, some of them are basically piles of rubble. Some of them are basically large chunks of metal, or fairly moderate-sized chunks of metal. With Gaia, you're able to do something we haven't done before. We've always before gotten at asteroids' masses through approximation, or with IDA we could get at it because of little dactyl orbiting around it. But you're doing something a little bit different.
We will observe masses because Gaia will be able to accurately determine the tiny deflections that are produced on the orbits of small asteroids when they encounter a big one. So this is a kind of very subtle and tiny gravitational effect that require an enormous astrometric accuracy that you cannot achieve on the ground. Gaia will be. And each one of the largest 150 asteroids will experience a number of close encounters with smaller guys. And so you can improve the accuracy in the determination of the mass by averaging over the outcomes of several events.
And to give you a sense of just how amazing this is, it's not Han Solo's asteroid belt out there. In general, if you're standing on any asteroid looking around with your eyes, you wouldn't be able to see any other asteroids. They're that far apart, typically 5 Earth-Moon radiuses in distance apart. And so these are minuscule gravitational tugs that you're able to measure. And it's amazing math and amazing imaging. Now, you were part of the Dawn mission, which cheated and orbited Vesta and got very accurate masses, but beyond just getting masses, it was able to figure out what this asteroid is made of, in part because of the instruments that you work on.
Yes, also thanks to the instruments, but also thanks to the fact that the mission was so different with respect to the other mission, because it was able to find a different API from the architect from the center of the asteroid, so it was able to improve the dimensional field. The asteroid itself was giving us the possibility to understand not only the mass, but the internal distribution of the mass. That means that you know how the asteroid is in the field. In the case of Vesta, we have finally the proof that it's with nanotons like that, and possibly the mantle and the planet. So it's really very similar to a small planet, very small because it's really activity object with this like the Earth or Mars and so on, but it's really similar to a planet. And then the instrument helped us in a lot of features, like the common feature that was not expected as many in this one. And moreover, the instrument we were able to be positional. So the instrument that we did that is made a lot of wonderful images in more than 300 bands. So we got to
And this is something new for us to think about. Even though Vesta is much, much smaller than the Earth's moon, it, in the process of forming, still was big enough to have the types of geological processes that form new minerals and end up such that it has a top layer, a lower layer, all the way through. It's really a fascinating object, and it's also very strange to look at because at some point in its past, it had a very violent collision that literally smushed in what is now its south pole and created wrinkle ridges about its middle. Has its violent history had an impact on the minerals that it has? And if you could speak to the camera, they like it.
So, the cycle was not affected by this violent, that we did not find clear evidence of glasses as on the moon, because indicated the collision in the atmosphere was rapid, because the velocity are low, so we do not have this speed change in the path. What we get is the possibility to see in the deep basin, so the installation of the every is this in this way was Intermediata, so we recognize so the other thing that is probably less relevant is continuous flux of the factors, possibly from the other that because that is in the and we recognize a lot of, let's say, that stuff all around that stuff that is connected with the material that is common among them. And this material is widespread, so in production, and moreover, this material has a lot of reach.
What's really fascinating is there's actually at least one instance of a crater where the material that is sprayed out from the formation of the crater has both dark minerals and bright minerals, and it's remarkable science to try and decouple what of this sprayed material comes from the impactor and what is below the surface material on Vesta that's been splashed out. And one of the other things that makes this interesting is the solar system has been kind enough to shower our planet with meteorites. And by studying these meteorites in the lab, we can say something that looks like this is made of these different minerals, and we can start to see if there's different families of asteroids, perhaps objects that broke apart in the past, and meteorites that come even from Vesta that we found here on Earth. Now, how have you been able to work to tie the laboratory results and the spacecraft results together?
I have to say that don't mention design. Reverse sample because we have in our lab a lot of material. Really, you have to know that, for instance, the moon rocks that we have on Earth is 1/10 of the best rocks that we have on Earth. So we are really very lucky because we have plenty of best rocks that can be studied in our lab. So we discovered a lot of things. We discovered, for instance, that was formed very early in the solar system. Was possibly the first object that we considered. So it's much more, it's older than the moon, it's older than the Earth, Mars, and so on. So it's really is a remnant of the formation of the solar system. And this is thanks to this rock, because we are able to make the radiation of the rocks. So we can state that Vesta was formed soon after the formation of the first aggregates in the universe.
And in about 8 more months, we're going to have data coming in from Ceres.
Yes, this is another story of what's massive. We think it's a good planet, you're right, and in the next 2 months we will arrive at Ceres and the other mission, just as we will arrive to the other planets. So I think that we will have a lot of fun with these two different planets. And in any case, Ceres is, we think that it's really different because we have evidence of active mind or materials
It's kind of amazing that people are beginning to speculate that there may be subsurface seas, subsurface oceans on Ceres, just like we're finding on Jupiter's moons and Saturn's moons.
There are several elements that can us keep for the moment there is a very good shape of Ceres that is can give us some indication that some surface ice and water that we could take there. There are the fact that the Ceres does not have a high elevation context. That means that you have a sentence that is completely work with the environment. So there are indication on this.
Yeah, one of the weird things about our solar system is small objects, because they don't have a lot of mass, don't have a lot of gravity. So really big mountains and cliffs and fault lines all have the possibility of existing on small worlds that can never exist on the large ones. And when you find a smooth moon or a smooth asteroid, you know there's something going on that's creating that not very cliffy surface. Now, I remind the audience, if you have any questions, please go ahead and ask them, and I'm going to ask our speakers to please be very loud. And as we look at getting more and more spacecraft sending back this amazingly high-resolution imagery from right there, and we have more and more Earth-Moon system close by orbiting spacecraft like Gaia, and I know Herschel's taken a number of observations. As we combine all of this data, what is the new big picture understanding of asteroids that's emerging?
I'd say there are several big questions. So we mentioned there's a link with the meteorites that we see on the ground. So linking the composition of those objects with space is still an open problem. The case of Vesta is a very specific one for which we are lucky to have a lot of information thanks to this incredible mission. But more in general, we have several other questions still open. For example, we mentioned the hypothesis that could modify the interior of the large asteroids. So we say that these objects could be differentiated inside. But when we look to the variety of spectral colors that we have, for example, in asteroid bodies that come from the breakup of these large objects, well, we would like to see then the signature of this variety, of this internal diversity. But in fact, there are just some few hints, but very hard to say if they are real. In general, we see the standards as homogeneous, spectrally homogeneous bodies. So I think this is really a big question, because we are touching a fundamental problem, a fundamental process in planetary formation. And I think that we really need much larger statistics. So this kind of survey missions or even surveys from the ground to better understand what's going on in general and how the planetary formation process works. Because in the end, we want to understand how this system works.
In general, with that, saying that asteroids are a very heterogeneous approach. We know for sure that among them there are some of the oldest samples of solid material that has survived since the early phases of formation of the planet system. So one of the major tasks in astrophysics is to be able to understand what are the processes that have been working and which may have caused some evolution of this unity matter, and to understand what are the objects that are still really close to their initial condition. These are the objects that we find in our laboratory as the oldest meteorites that give you information about the age of the solar system. We know that the age of the solar system because we want to talk about it. We want to understand, better understand where these objects come from. Are they pieces of comets or asteroids?
And one of the things that has amazed me the most is I remember as a small child we were sometimes taught that the asteroid belt was made from a planet that got smashed apart. And now we're coming more and more, it seems, to the realization that there were a family of larger objects that got smashed apart. And can you start to work backwards to at least say more and more objects, how they fit together in the history as we learn more of the spectroscopy and the dynamics?
This is really it's a wide subject.
Yeah, well, I can just hint a couple of say, piece of evidence that could help us. First of all, the distribution of the color of asteroids that it results from a kind of a dynamical mixing of what was there at the beginning. So how was the solar system at the beginning? It was a mix of gas and dust. And the most recent theories say that probably the most efficient way to form the first protoplanets, or planetesimals, how they call it, that was to have a solid material concentrated by the gas in certain regions, and then this concentration could have collapsed to directly form large asteroids, which were the parents of the grandparents maybe of the population that we observe today. And then there were episodes of rather mixing of chaoticity in the motion that mixed the positions and the orbits of those bodies. And we observe today still the signature of the initial distribution of these objects. But of course, this is probably just 1% of the whole population that was in the asteroid belt at the beginning. So we are remaining with something that is 1%. We know several 100,000 objects, but we have the physical properties for maybe a few hundreds of them. So it's just like studying the population of the entire population of animals on Earth, just from picking up a few dogs, a few cows, and trying to understand all the rest. This is the situation, I would
So as we prepare to wrap this up, if you could say what that piece of data you're most hungry to get is, I'd love to hear what you're waiting for.
We're hungry, we want to obtain everything. This is so we want to better know all the properties of the objects that are there now that we want. We want possibly to discover new ones. And what is important, after the science is important in two major respects. One is purely theoretical, for understanding the history of formation and evolution of the solar system. This is one. And then there is also the practical application of the fact that this is very popular subject that should not be properly overemphasized, but does exist. So,
and I say what to that. I think that the statistical study of the extreme, but also the detailed study of the largest is very important. Because those objects are really the grandparents of the large population that we see. We have very few objects, really more or less, that are maybe impacted. So we need to study them in order to figure out how the other grandparents were behaving. So I'm really happy to for the data we studied in massive. Especially for teams, and really to see the results and see basically to get clear of the water, the soil, the ocean, the salt in the ocean that can give us some more chance to see something.
And this time next year, we will probably all be together again, except instead of being in Lisbon, we will be in Nantes, France. And we will have data from series, raw and still being worked on, and we will continue to gather more and more data from Gaia, allowing more and more orbits to be refined. And we are just going to keep increasing our understanding. And if you would like to help us explore the asteroids, well, this hangout is hosted by CosmoQuest, and we provide you the opportunity to help us work with the Dawn mission to map out the surface of the asteroid Vesta, to find the fault lines, find the craters that have bright colored blankets around them, and to do the science that those of us in this room and those 700 of us at this conference, we're just not enough people to do it all on our own. So help us explore our solar system, and thank you for joining us this afternoon. And thank you for joining us online.
Thank you. Thank you. Bye-bye.